This is Math 2 7.1a notes. That's Unit 7, Lesson 1a, and the title is Radicals. Simplify. Number 1, the square root of 24. That should look familiar to you. We have seen that before. We've done this back in the beginning, like the first week of back to school. And I taught you back then to break these down. You can use 3 and 8, 6 and 4, 12 and 2. I'm going to use 6 and 4. Neither of these are prime, so I'm going to do 2 and 3. Those are both prime, so I'm going to circle. And 4 is 2 and 2. When you do your factor tree, it does not matter what you start with, you will end up in the same place. So regardless if you use 6 or 4 or 8 and 3, you should have 2, 2, 2, and 1, 3. And if you remember correctly, we circle our pairs. So there's a pair here, comes out as a 2. Those are not pairs, so they're going to get left in. So that's a 2 root 2 times 3 is 6. That is your final answer, 2 root 6. That should feel like review to you. All right, number 2, 3 square root 128. Prime factor tree, so I break it down using 2. You can plug it in your calculator. You can actually do that in your head. 12 divided by 2 is 6. 8 divided by 2 is 4. 64. Because that is a perfect square, I'm going to use 8 and 8. You could use 32 and 2, but I'm using 8 and 8, and the reason is because those are pairs, I do not have to break it down. I'm circling them. I know they're not prime, but because they are pairs, I can stop. And I have shown you that shortcut before, is once you find pairs, stop. You don't have to continue. Now technically you can. You can continue breaking down to all the prime factors, but it's going to work out the same, and this is much quicker. Okay, so that comes out as just 8. The 2 stays in. 8 root 2 is the final answer. If you don't like that, I can show you how to do it all the way down to all the 2's, and you can go from there. We can do that in class. Number 3, square root of 12 times the square root of 24. Because they are, it's multiplication, I am allowed to multiply them in 1, 200. Technically, you do not have to do that. You break up the 12, break up the 24, and just write them all under 1. The only reason I multiply them together is hoping it's a perfect squared. It's not, so then I'm going to break up. Now, you could break up 12 and 24 because that's exactly where it came from, but I'm going to use 2 and 144. And 144 is a perfect squared, so it is 12 and 12. Now, these are not primes, but because they're a pair, I am allowed to stop. If you don't like that, keep breaking all the way down. 12 is a pair, comes out as 12. 2 is left in, and you get 12 root 2. Now, because I do want to jump back to number 2. There was a mistake made on number 2. I'm hoping you caught it and thought, what the heck is she doing? The mistake that I made is a mistake that kids make quite often. They do all this, they do exactly what I did, and bring out the, 8, and leaving in the 2 and calling it done. Now, unfortunately, if you were to do that on a test, you would not receive full credit. That is 8 root 2, but remember that 3 that was right there? It's 8 times 3 root 2. So your true final answer is 24 root 2. Okay, moving on. Number 4, square root of 18 squared. Different ways of thinking about it. Root 18 times root 18. Because quantity squared means you write the base twice. That's what I end up with. Now, you do not, some kids will multiply 18 times 18, get 324, and then break it down to 18 times 18, and there's a pair. Your answer is 18. You do not have to show this work right here. I'm hoping you recognize, hey, that's a pair. It's going to come out as just 18. You don't need to know what the product of 18 and 18 really is. These are called inverse operations, square roots and squares. They undo each other, and you're left with whatever's on the inside. Okay, number 5, root 56 quantity squared. Same concept. These are inverse operations. They undo each other. You're left with the inside. So I know my answer is going to be 56. Now I'm going to show you mathematically. You have root 56 times root 56. You don't have to show all this work I'm about to show. I'm just showing you how it works. It is a pair. It comes out as just 56. I'm hoping eventually you can just say, oh, inverse operations, they undo each other. You're left with what's on the inside. Okay, number 6, 3 root 5 quantity squared. Now, I am going to kind of use inverse operations here, but the 3 is not in a square root, and that does change things a little bit. So I am going to write the base twice, 3 root 5 times 3 root 5, because that's everything in the parentheses. And because it's multiplication, multiplication is commutative, I'm allowed to rearrange everything. 3 times 3 times root 5 times root 5. 3 times 3 is 9. Now I'm hoping you don't have to say 25, you don't have to think of 25. Root 5 times root 5 is just 5. Why? Because root 5 times root 5 is root 25, and the square root of 25 is 5. Don't even think about the 25 though, just know it's a pair, so it's 5. And 9 times 5 is 45. A really quick side note, some people will do it this way: 3 root 5 quantity squared, and you distribute the exponent as long as there's no plus sign in the middle, and there's not. 3 squared root 5 squared. 3 squared is 9. Those are inverse operations. They undo each other, leaving behind just the 5, and 9 times 5 is 45. Whichever method makes sense to you is the method you're going to want to stick with. Okay, number 7, square root of 49 over 16. Now, multiplication and division, you are allowed to put together like we did over here, combine them in one radical, or you can rip them apart to separate radicals. It's up to you. As long as it's multiplication or division, you are allowed to do that. I am going to separate this. Luckily, they're both perfect squares. Square root of 49 is 7. Square root of 16 is 4. 7 over 4 does not reduce. That is my final answer. Okay, last piece. I'm going to write down that I want you to rationalize. This is something we talked about, again, that first week of school. Number 8, 1 over root 5. Now, if you remember back then, I told you radicals were not allowed in the denominator. It's mathematically incorrect to leave them there. So what did we do back then? We multiplied top and bottom by whatever radical was in the denominator. So that's root 5 over root 5. Why? Because root 5 over root 5 is 1, and if you multiply anything by 1, it doesn't change. It's a multiplicative identity, and those are inverse operations, or there's 2 of them, there's pairs, however you want to think about it. Root 5 times root 5 is 5. 1 times root 5 is root 5. Root 5 over 5. I cannot reduce those because that's a radical. That is not that. There is the final answer. All right, number 9, root 2 divided by root 7. Now, what do I multiply by? Root 2 or root 7? There's 2 radicals on that one. First off, I can't reduce. You should check that first. Can't reduce and can't have a radical. So it's the radical of the denominator. Why? Because that's the one I want to have a pair. That's when I want to make a pair so that the radical is gone. Root 7 times root 7, without saying 49, without thinking 49, I'm hoping you understand it's just 7 because it's a pair. Now, your brain, it's okay if you process root 49 and root 49 is 7, but eventually when these numbers are bigger, like that one, you don't want to have to multiply 56 times 56. Do you see that? Okay, root 2 times root 7 is root 14. I'm allowed to put them together because they're both in radicals. So I have the square root of 14 over 7. I'm not allowed to reduce those because one's in a radical and one is not. And number 10, 3 divided by root 11. I cannot have a square root in the denominator, so I'm going to multiply top and bottom by root 11 because that's the radical I'm trying to get rid of. Without knowing what 11 times 11 is, we know it's a pair, so it's just coming out as 11. These are not both in radicals, so I cannot multiply the two numbers together and call it like 33 or root 33. I was able to here because they were both in radicals, but that's not the case here. So I end up with this. These two numbers cannot reduce because one's a radical, one is not. Those two numbers I am allowed to reduce if they reduce, but 3 and 11 do not reduce. So this is it. This is your final answer. Okay, that is it for this lesson. I will discuss more of this with you in class.